In today's video, we are going to look at some series of qualitative analyses from paper 2 of the chemistry CSEC exams. So let us begin. A student carries out the following test on substance Z and makes the observation recorded in table 1 below. Complete table 1 to show all possible inferences and write equations where required. Part 1. Heat a small sample of solid Z gently in a dry test tube. And the observation was that a pungent gas evolves which turns damp red litmus paper blue. There are two pungent gases or choking gases that we should consider when looking at qualitative analysis. They are sulfur dioxide, which is acidic, and that means it turns blue litmus paper red, and ammonia, which is basic or alkalinic, which turns red litmus paper blue. So here we definitely know that ammonia gas was produced based on the observation there. What that means, so the source of ammonia should come from the fact that the ammonium ion is present. So due to the presence of the ammonium ion, that would have liberated the ammonium gas when it was heated in the dry test tube. Part 2. Add approximately 2 centimeter cubes of aqueous sodium hydroxide to a sample of solid Z and warm. The observation is that a gas evolves which turns dense white fumes, which forms dense white fumes with hydrogen chloride. Now when ammonia reacts with hydrogen chloride, it forms ammonium chloride. Again, this confirms that ammonium ion is present, and so the ionic equation, so ammonium ion is confirmed. And the ionic equation for that reaction we are interested in the hydroxide ion from the sodium hydroxide and the ammonium ion to produce the ammonia gas. So here we have the ammonium ion which is in the solid form, plus the hydroxide ion which would be in the aqueous form, and that would give ammonia gas and some amount of water liquid being present. And here, so let us see if the ionic equation is balanced. So we have 5 hydrogens over this side, and we also have 5 here. We have 1 oxygen, and 1 nitrogen, 1 nitrogen. So the equation is balanced. The next part of the question: dissolve a spatula full of solid Z in approximately 10 centimeter cubes of deionized water. Divide the resulting mixture into 3 portions for test 4 to 6. And the observation is that a pale green solution is formed. The mere fact that we saw a pale green solution, iron 2+ is present. So the iron 2+ ion would be present because iron 2+ form green solution when added to water or other mixtures such as sodium hydroxide and ammonia, aqueous ammonia. Part 4. To 1 portion of solution Z from 3 above, add aqueous sodium hydroxide dropwise until in excess. So when we add the sodium hydroxide dropwise, we saw that a green gelatinous precipitate forms. This means that iron 2+ is present. Iron 2+ is present. Then what happened in excess? When in excess, the precipitate is insoluble in excess sodium hydroxide, so the precipitate remains. So iron 2 plus is confirmed there. Iron 2 plus is confirmed. Now they want you to write an ionic equation for that reaction. What we are interested in is the iron 2 plus and the hydroxide ion. So it's Fe2 plus. Let me change that color. So we need Fe2 plus, and it was administered in the aqueous form, plus Fe2 plus the hydroxide ion OH, and that produced the precipitate iron hydroxide FeOH. And since it's the oxidation, the 2 plus oxidation state, the 2 go outside the bracket of the hydroxide ion and you put your solid. So that is how you know whether what the state symbols are. If the solution is soluble, then you should put aqueous. If it's a pure liquid like water or a melt, you should put the L. But once it's a precipitate or an element in its pure state, apart from mercury, you know that mercury is one of the only metals that, or one of the few metals that form a liquid at room temperature. Other than that, everything else in its elemental state would be a solid. PPT, if it's a precipitate, you should put solid in the bracket. And so that is how you know how to put what to put the state symbol, which state symbol should be there. And to balance this equation, you put a 2 beside the OH to balance the 2 OHs that are on the right hand side of the equation. So that's the ionic equation. Part 4 of the question says, or of the table, to another portion of solution Z formed from 3 above, add a dilute nitric acid followed by aqueous silver nitrate solution. Once we're adding dilute nitric acid and silver nitrate, we know that we're testing for the halides. Specifically, we're testing for chloride ions, the bromide ions, and the iodide ions. Here, they are saying that no observable reaction was seen. So that, what can we infer? We can infer that the chloride ion, the bromide ion, and the iodide ions are not present. Write that properly, that word ion. And the iodide ions are not present because there wasn't any observable reaction that would suggest that these ions would be present. Okay, all right, the next part says, to another portion of solution Z from 3 above, add barium nitrate followed by dilute nitric acid. Barium nitrate, and then our observation is that a white PPT forms in dilute acid, insoluble in dilute acid. That white PPT is due to the sulfate ion being present. So it is let me change that color again. So it is the sulfate ion being present. When barium reacts with the sulfate, the white PPT of barium sulfate is produced, and we know that all sulfates are soluble except barium, calcium, lead, and silver. So the barium sulfate, so the sulfate ion is present. So once you see barium nitrate followed by nitric acid, you know that we are testing for the sulfate ions, and we got a positive observation, which is the white PPT, because barium sulfate is a white solid. And the ionic equation is, we are interested in the barium ions as well as the sulfate ions. Since ionic equation involve both the negative ions and the positive ions, and this produce barium sulfate. Again, it's a PPT, so a solid would be the state symbol, and for sulfate it was administered in the aqueous form, so you put AQ down there. Same thing for the barium sulfate, aqueous. The equation is already balanced, so don't need to add anything else. So that would complete the table for this particular year. Moving on to May-June 2005. Y is a mixture of two salts. A student carries out a number of tests on a sample of Y. The observations are recorded in table 1 below. You are required to fill in the inferences that can be made based on the observations recorded. Part I, heat a small portion of solid Y in a test tube, gently at first and then strongly. A colorless gas evolves with a choking odor. Then another observation states that it turns acidified potassium dichromate solution from orange to green. This information tells me that sulfur dioxide was produced. Sulfur dioxide was produced. And sulfur dioxide would act as a reducing agent, where it changed potassium dichromate from orange to green. So sulfur dioxide is oxidized in the process while it reduces potassium dichromate. And if the SO2 gas, if the sulfur dioxide gas is produced, it simply means that the SO3 2- ion is present. Okay. Part 2. The remaining portion of solid Y. To the remaining portion of solid Y, add 20 centimeter cube of distilled water. Stir to dissolve and filter. Collect the filtrate and divide into 3 equal portions. Here they're saying that the filtrate is pale green in color. Once we see pale green, we know that iron 2+ is present. Okay, all right. Part 3. To the first portion of the filtrate from B above, add aqueous sodium hydroxide slowly until in excess. And the first observation is that a green precipitate is formed. So this means that iron 2+ is present. And after, insoluble in excess aqueous sodium hydroxide. This iron 2+ is confirmed. Iron 2+ is confirmed. And so they want you to write the ionic equation for the reaction, and that is the Fe2+ aqueous plus the hydroxide ion, some space there, the hydroxide ion to give iron hydroxide, which is the solid in this case. Again, we need to balance the ionic equation by putting a 2 there. And this is also aqueous. Alright, this seems very dull, so let me try and rewrite that with a brighter color. So it would be Fe2 plus the hydroxide ion to give FeOH, 2 solid, and the 2 right here to balance the equation. This should be aqueous, this should also be aqueous. Okay. Part 4, to the second portion of the filtrate from B above, add aqueous silver nitrate followed by aqueous ammonia. So adding silver nitrate, it means that we're testing for the halides, right? Followed by ammonia. All right, so first the observation states that white precipitate is formed. Chlorine, or the chloride ion, forms the white precipitate, so that means the chloride ion is present. And they are saying that it is insoluble in aqueous ammonia, and this confirms the chloride ion. So the chloride ion is confirmed, because the chloride ion would be insoluble in aqueous ammonia dropwise, but it would be soluble in excess ammonia, and we can use that to confirm that chloride ion is indeed present. Now, for the halides, chlorine, the chloride ion, produce a white PPT, the iodide ion would produce a yellow PPT, and the bromide ion would produce a cream PPT. So that's what we can use to distinguish between the different ions. Part 5, to the third portion of the filtrate from B above, add aqueous barium nitrate followed by aqueous silver nitrate. And we should expect a white PPT. See, the white PPT is there. And so from that white PPT, it is also observed that precipitate readily dissolve in aqueous nitric acid with the evolution of a colorless gas with a choking odor. So that confirms the presence of the sulfate ion. So SO4 2- is present, and for this part of it, SO4 2- is confirmed based on the fact that sulfur dioxide was produced. Okay, so on to the next part of the question. On to the next part of the question, which is January 2006. It says a student conducts a number of tests on an aqueous solution of compound P. Some of the observations and inferences made are recorded in Table 3. You are required to complete the missing observations and inferences. So let us look at one. To a sample of solution P, dilute nitric acid is added, followed by a few drops of silver nitrate. And as mentioned before, once you see silver nitrate with nitric acid, you know that they are looking for the halides. And the inference state that the chloride, bromide, and iodide ions are not present. So what would be the observation? No observable reaction. No observable reaction. Part 2. To a sample of solution P, a few copper turnings are added, followed by concentrated sulfuric acid. Brown fumes evolve which turn moist blue litmus paper red. In this case, we know that the brown fumes belong to the nitrogen dioxide that was produced. So nitrogen dioxide was produced. But what else is that saying? It is also saying that the nitrate ions are suspected, because the nitrogen dioxide must be coming from, or most likely be coming from, the nitrate ion undergoing some form of decomposition. So the nitrate ion are suspected. Part 3. To a sample of solution P, a few drops of acidified aqueous potassium permanganate solution are added. The potassium manganate solution changes from purple to colorless. What would change potassium permanganate from purple to colorless? We know that the sulfur dioxide is the culprit responsible for that. So sulfur dioxide gas was produced. And if the sulfur dioxide gas was produced, it simply means that the sulfite ions are suspected. Because the sulfur dioxide came from the sulfide ions. Okay? And part 4, to a sample of P, aqueous sodium hydroxide is added until in excess a green precipitate forms. The only green precipitate form from the cations that is required at your level is the iron 2+ ion. So as the iron 2+ ion is present, the precipitate is insoluble in excess sodium hydroxide. It simply means that what this is saying rather is that the iron, when added the sodium hydroxide in excess, the green precipitate remained. So Fe2+ is confirmed. It's confirmed, and they require an ionic equation. So let me use a different color to represent the ionic equation. And the ions that we are interested in are the Fe2+ ion and the hydroxide ion. When those combine, iron hydroxide, which is the insoluble green PPT produced, you put the symbol, the S symbol, to indicate the state that is present there. Aqueous, Fe2+ taken from the aqueous mix, so aqueous is there. And to balance the equation, we have 2 hydroxide over here, so we need 2 over here as well. And so that would complete the table for this particular year. Okay. So part for May-June 2006, the table says complete the table below for tests carried out on solid Q. Part I. To solid Q, add water, stir, filter, and then divide the filtrate into 4 portions. Retain and dry the residue for test 6 below. Moving on to part 2, to the first portion of the filtrate from 1 above, add aqueous sodium hydroxide until in excess. The inferences stated that aluminum ion, lead ion, zinc ion, and calcium ions are present. In excess, the aluminum ion, the lead ions, and the zinc ions are present. That's for in excess. excess. So let us look what the observation should be dropwise. For dropwise, we should expect a white precipitate, a white PPT formed. So that's what should expect for dropwise. In excess, calcium is insoluble in excess sodium hydroxide. The calcium ion, it is insoluble. However, in excess sodium hydroxide, aluminum, lead and zinc ions are soluble, or they dissolve in excess sodium hydroxide. So you can write soluble solution formed in excess. Right, so those ions would dissolve in excess sodium hydroxide. So part 3, to the second portion of the filtrate from high above, add aqueous ammonia until in excess, and a white PPT appeared. Now for dropwise, so for dropwise, calcium is soluble in ammonia dropwise. However, aluminum ions, Al3+, lead ions, Pb2+, and the zinc ion, Zn2+, those would be present when dropwise. Okay, now the observation stated that the precipitate soluble in excess aqueous ammonia, of these 3 ions that were insoluble in excess, only zinc appears to be soluble. Of these 3 ions that were insoluble in excess, only zinc appear to be insoluble. Only zinc is expected to be soluble in excess, meaning that it dissolved in excess ammonia. So zinc 2+ ion is confirmed because it is soluble in excess, while aluminum and lead, they are insoluble in excess. Only zinc would form a soluble solution or a colorless solution in excess ammonia. Part 4, to the third portion of the filtrate from one above, add aqueous potassium iodide. A yellow PPT is formed. So once we add the aqueous potassium iodide and a yellow PPT form, we know that lead 2+ ion, Pb2+ ion is present, and the equation for that would be Pb2+ plus the hydroxide ion OH minus give Pb hydroxide, would give lead hydroxide, and that is a solid because it's a precipitate would form from that. Again, balancing the equation, put a 2 beside the OH there. Don't forget the state symbols. So it would be aqueous right here, and of course the solid over there. Part 4, to the fourth portion of the filtrate from one above, add aqueous silver nitrate. Followed by aqueous ammonia. Remember, once we're adding silver nitrate, we're testing for the halides, but they said no observable reaction was present. So we know that the chloride ion, the bromide ion, and the iodide ion are not present. Okay. To the dried residue from I above, add dilute nitric acid, warm, filter, and then divide the filtrate into 2 portions. So here we have a vigorous effervescence observed from the addition of the dilute nitric acid, a gas eval which turns lime water cloudy. So mere fact that we say vigorous effervescence, which means that carbon dioxide was produced and the carbonate ion is present. So carbon dioxide was produced and the carbonate ion CO3 2 minus ion is present. Now, carbon dioxide is the gas that turns lime water or calcium hydroxide milky or cloudy, and the ionic equation that we are interested in for this particular reaction would be between the carbonate ion CO3 2 minus plus H plus from the acid aqueous, and that would give carbon dioxide gas and water. Let's see if the equation required any balancing. So we have 3 oxygen over here, so we need a 2 to be beside H plus right here to balance the equation. And the state symbol for water should be liquid, and they said that to the dried residue, so this should be a solid. Okay, let me write that solid properly, the S properly, S solid. Okay, scribble that properly, S for solid. All right, part 7. To the first portion of the filtrate from 6 above, add aqueous sodium hydroxide until excess. So what do we expect? Copper, the inference is stating that copper ion is present. And if copper ion is present, what should we observe? We should observe a blue precipitate being formed, because dropwise copper ion is insoluble in the sodium hydroxide dropwise. So a blue precipitate is produced. Blue PPT formed. All right, and then in excess, the blue PPT would remain in excess. The blue PPT remained in excess. Okay, now the next part says they want you to write an ionic equation, and the equation that we are interested in is the copper hydroxide Cu2 plus the hydroxide ion from the sodium hydroxide, and that would produce copper hydroxide, which is the PPT, and so a solid would produce. This is aqueous. This was the dried sample, so we expect copper to be in the solid state, and of course you have to balance the equation right there, the ionic equation. Okay, and part 8, to the second portion of the filtrate from 5 above, from the 6 above, add aqueous ammonia until excess. So we know that copper with aqueous ammonia form a blue PPT. A blue PPT is formed. PPT is formed. and in excess ammonia, you have a dark blue solution would produce, which is the copper ammonium complex. So in excess, a dark blue solution is produced. Dark blue solution formed. That's what happened in excess. Okay, so let us look at the next part. This is January 2007. Complete table 2 below by writing the inferences for test carried out on solid W. A sample of solid W is moistened with sodium hydroxide solution and the mixture heated. Moist red and moist blue litmus are held at the top of the test tube. So these are the observations. A pungent gas evolves. Red litmus paper turned to blue. So the pungent gas evolve would be due to ammonia. Ammonia gas is present. Write that properly. Or ammonia gas was produced. The ammonia gas was produced. And for the next part, the ammonia gas is confirmed. Which means that the ammonium ion is present. NH4 plus ion, ammonium ion is present. Okay, part 2. To an aqueous solution of W, a few drops of acidified silver nitrate are added, followed by aqueous ammonia. A white precipitate is formed. The precipitate dissolves in aqueous ammonia. So if the white precipitate form, that means the chloride ion is present. So the Cl ion is present. And if it dissolves, it means that the Cl ion is confirmed. The ionic equation for that would be between the silver ion, Ag+, and the chloride ion to give the precipitate, the white PPT, silver chloride, solid. This would be aqueous and aqueous. Okay. Part 3. To an aqueous solution of W, a solution containing barium ions is added. The white PPT is formed. If a white PPT is formed, it means that the sulfate ion is present. The sulfate ion is present because barium sulfate, which is the white PPT. So the sulfate ion from the solution would react with the barium ion to produce the white PPT of barium sulfate. Part 4. Dilute hydrochloric acid is added to the mixture from 3 above. Observation is that the precipitate is insoluble in the acid. And we know that barium sulfate is insoluble in hydrochloric acid. And so that would produce barium chloride. So the ions that we are interested in is the barium 2 plus ion plus the chloride ion to give barium chloride, BaCl2. That's also a precipitate. That's aqueous, it's coming from the acid, and this is a solid coming from barium sulfate. The equation is to balance, so we put a 2 here. So that would be the ionic equation from the reaction that produced barium chloride. Okay. On to the next question. May, June 2007. A student carries out the following test on a solid Q and makes the observation recorded in table 2 below. Complete table 2 to show all possible inferences and write ionic equation where required. Part I. A small sample of Q is heated in a dry test tube. A brown gas evolves which turns moist blue litmus paper red. Another gas evolves which rekindles a glowing splint. Okay, so the brown gas evolved, we can infer that nitrogen dioxide was produced. The gas that rekindles a glowing splint also indicate that oxygen gas, O2 gas, was also produced. So what can we infer from this? We can infer that the nitrate ion is present. Alright, because that seems as if it's some decomposition. So the nitrate ion is decomposition of the nitrate. So the nitrate ion is present. A portion of Q is dissolved in approximately 10 centimeter cubes of deionized water. The resulting solution is divided into 3 portions from test 2 to 4. Part 2. To 1 portion of solution Q from above, aqueous sodium hydroxide is added dropwise until in excess. The observation is that a white precipitate is formed. Now the precipitate is soluble in excess sodium hydroxide. The white precipitate that is formed first when it is added dropwise indicate to us that aluminum Al3 plus, Pb2 plus, zinc 2 plus, and calcium 2 plus are present. Okay, now the precipitate is soluble in excess. Of the 4, only 3 are soluble in excess, and those are aluminum 3 plus, lead 2 plus, and zinc 2 plus. 2 plus are present. So these are the ions that remain when excess sodium hydroxide is added. Part 3. To another portion of Q from above, aqueous ammonia is added dropwise until in excess. When the ammonia is added dropwise, a white precipitate is formed. Calcium is soluble in dropwise ammonia, so it means that only aluminum, and these are all the white PPT, calcium, lead, zinc, aluminum, those form the white PPT. So pay close attention. Please ensure that you know those like the back of your hand, because your examiners will want to quiz you heavily on these. So there are 4 PPTs, white PPTs, that form from either aqueous sodium hydroxide or aqueous ammonia. And as mentioned again already, aluminum, lead, zinc, and calcium, those are the white PPTs. that would form when interacting with lead and aluminum. That would interact with sodium hydroxide and ammonia. So the white PPT that is formed would be aluminum, lead 2+, and zinc 2+. So those ions are present. Okay, the precipitate is insoluble in excess ammonia. So when we add excess ammonia, only 2 precipitate of these 3 white precipitate would be insoluble, and they are aluminum 3+ and lead 3+. Only those 2 would be insoluble in excess ammonia are present. Zinc is soluble in excess ammonia, so we can rule out zinc given that it's a precipitate that form. Now part 4, to another portion of Q from above, aqueous potassium iodide is added, and then we observe a yellow PPT form. And once we see a yellow PPT form, we know that when lead react with potassium iodide, when the lead ion react with the iodide ion, a yellow PPT is formed. Aluminum also react with the iodide ion, but no observable color change in the PPT resulted from it. So we know that if you see a color change and it is yellow, you know that is lead. Okay, and it can be potassium iodide, it can be sodium iodide. It's the iodide ion that we are interested in. Okay, so this means that lead 2+ ion is confirmed. And the equation would be lead 2+, Pb 2+, plus the iodide ion, since that's what we're interested in, which is the PPT that was formed, to give lead iodide, PbI2, and that's a solid. This is aqueous. You need to balance the equation, so put a 2 right there. Okay, and this should be aqueous because it was dissolved and put in 3 portions. Okay, so that would be the ionic equation for the lead and for the lead iodide formation. Part 5 says, suggest the possible identity of Q. We suspected the nitrate to be present based on the observation there, and we confirm lead down here. So most likely this is lead nitrate. Q would be lead nitrate, PbNO3 2, which is lead nitrate. Okay,